So up next, we're going to sort of look at some exponential models, okay? And we're just going to look at the exponential ones because I think they're a little bit more interesting. The textbook has a few sections on different models that use logarithms. We already saw that decibels, the unit that measures how loud something appears to us, that those are on a logarithmic scale, right? The Richter scale for measuring earthquakes is logarithmic, as well as actually the pH scale for measuring how acidic or basic a acid or base is, right? Um, but we're going to take a look in a little bit more depth into models that use exponentials, okay? And the first one we're going to take a look at is exponential growth. In particular, we're going to look at a concept called doubling time, okay? And there is a way that doubling time is most often brought up, and that is the speed at which bacteria grow. And given the state of the world, even though COVID is a virus, not a bacteria, I kind of want to escape from that world for a little bit and not build a model based off of bacteria. So let's say there's this, Mr. Willy Wonka has a new popcorn machine, right? And this popcorn machine is crazy efficient, okay? So we'll say the Willy Wonka popcorn machine. It's not how you spell popcorn, okay? We'll say, just for the sake of construction, right, it's got an infinite amount of kernels in there, right? It's never going to run out. This thing is, totally idealized, right? And we'll say that the amount of popcorn, okay, doubles um, every, and the traditional unit here is A, okay? And we'll just say units of time to build a general model. Maybe there's a minute speed, an hour's speed, etc., right? So let's take a look at how many pieces of popcorn this thing's going to make, okay? So at t equals 0, right? Let's say we have, some number of popcorns, right? And not, okay? Well, after a units of time have passed, right? Let's say for now hours, right? Say we have a hours, okay? Well, it's going to double, right? So we should have 2 times n naught pieces of popcorn, right? What if we wait another a hours? Well, then at t equals 2a, right? We have 2 times 2 times n naught, right? Because it doubles. Or if you prefer, 2 squared, right? At t equals 3a, we're going to have 2 cubes, right? Because we double again, okay? And if we put all this together, we end up with the exponential growth equation, right? Based on doubling time, okay? And that's this equation right here. So my number of, pieces of popcorn or bacteria or whatever as a function of time, well, it's the amount I start with, okay, times 2 to the amount of time that has passed divided by this constant a, right? Where we have this n, again, that's our initial population, right, slash amount. T is the time since we started. A is the doubling time, right, for whatever we're dealing with. And it's sort of important to note that T and A must have the same units, okay? So I've cooked up a little example for you here. We'll say Wonka's Magic Popcorn Machine doubles the amount of popcorn you put in every 3 hours, okay? We're working at a big old movie theater, you know, and we start with 1,000 pieces of popcorn. I don't think I quite thought through the physical implications of this, but this is Willy Wonka, right? He can kind of do whatever he wants. Okay, so let's say we start with 1,000 pieces of popcorn. Okay, part A, we want to create a model for the amount of popcorn after T hours. Okay, we're asking how many pieces of popcorn are there after 15 hours, and then how long until we get 10,000 pieces of popcorn. Okay. So we'll take these just sort of a bit at a time, starting with part A, right? If we remember, our model is going to take this form, n of t equals n naught t to the 2 over a, okay? And we just need to fill in all of the various things, right? Our initial number, the size of our, initial population, right? We have 1,000 pieces of popcorn in our population. And then we have 2 to the, it looks like t is our variable, and 3 is our doubling time, okay? I guess we'll put a little dot there to say that we're multiplying those together, okay? For part B, we're looking for the number of pieces of popcorn after 15 hours, okay? And that's going to be n of 15, right? So we're going to do 1,000 times 2 to the 15 over 3, right? 15 over 3 is 2 to the 5, which is 32. So 32 times 1,000 is a whopping 32,000 pieces of popcorn. That is a lot, okay? And then part C, okay, we're looking for how many hours until they have 10,000 pieces of popcorn. So we're going to set up 10,000 or 100,000, and that's going to equal, well, 1,000 times 2 to the t over 3, okay? And now we want to solve this for t, right? So what we can do is we can divide both sides by 1,000, right? That's going to give us 2 to the t over 3 equals 100, okay? We want to take some logarithms here to isolate this exponent. We'll do log base 10 because it will clear up this nicely, and that means we could put it into a calculator should we wish. So then that's going to give us that the log of 2 to the t over 3 is the log of 100. But in this case, this is just going to spit out the number of zeros, right? And we get t over 3 as log 2 times 2, okay? And solving for t, we have t is 6 over log 2 hours, okay? If you're curious, go ahead and throw that into a calculator. But as we've said before, these exact forms are preferred, okay? So now one of the things that I want you to think about is we just looked at modeling this in terms of doubling time, okay? But what about tripling time? There's nothing stopping us from looking at it that way, and we could look at quadrupling time, or the time it takes for it to multiply by 10, right? That would just change the base of our exponential. So in light of that, right, what happens if we use e, okay? okay? Well, one of the beautiful things about E, okay, is the way that it handles change like this, okay? And again, I know I kind of harp on this a lot, but all of this will be fully explored in calculus. The YouTube channel 3 Blue 1 Brown has a lot of really interesting content based around E that he kind of did, I think, last summer. That stuff is super interesting if you're interested more in like, sort of the weirdness and the beauty going along with E. But what E allows us to do is model the relative growth rate, okay? And what the relative growth rate is it expresses the growth rate as a proportion of the population, okay? So we can say, oh, what if, this certain population every hour grows by 40% of its population. Well, we wouldn't have a way to plug that in, very easily at least, to plug that in to this model, right? But one of the nice things about E is it allows us to do a thing like this, right? N of T is my initial times E to the RT, right? Where this R, this is my relative growth rate, okay? And this does look a little bit, similar to the PE to the RT, and that's because it's sort of the same idea, right? The interest rate is our relative growth rate, okay? So I've got an example here for you. Okay, so let's say that a population of rabbits starts at 500. Okay, you have this group of biologists sort of watching them, and they know that the relative growth rate is 40% per month. Okay, and we have 3 questions here, right? 1, find a population, or find a function that models the population. After how many months will the rabbit population reach 80,000? And then we want to sketch a graph of the model. Okay, so going through these one at a time, part A, we want to find a function. Well, we're given this in terms of relative growth rate, right? So we can write this in terms of relative growth rate, and not e to the RT, right? That's our general form. We can write a specific one. My initial population is 500, and my growth rate is 40%, or 0.4 times time, where in this case time is measured in months. For B, we're looking for how many months until the population reaches 80,000, okay? And so in this instance, we're looking at where does 80,000 equal 500 e to the 0.4t, okay? Dividing both of these sides by 500, we get e to the 0.4t. Looks like that equals 160. So, as before, we're going to take the natural log of both sides, dropping that down and canceling my natural log of e. We get that 0.4t is the natural log of 160, okay? Or that t is the natural log of 160 divided by 0.4. This is our exact answer. For those of you who are calculator curious, 12.68 months, or just over a year, okay? And then C, we want to draw a model. Well, I have 2 points of information on this guy already, right? I have my initial population, which I guess we'll put right there, right, where this is my t-axis. At t equals 0, we have 500 rabbits, right? And then at t equals 12.68, measuring in months, we're going to have, let's put this right there, 80,000 rabbits. Okay, and our model is going to look a little something like that because this is an exponential. Okay. Notice that we don't graph anything back here, right? It doesn't make sense for us to have negative time, and we have our important pieces of data labeled on our graph. All right, up next, we have one last example in this sort of, comparing different growth rates section. We'll say that Wonka Factory is sort of using this magical popcorn machine, right? They developed this self-replicating chocolate bar, right? Which, however big it is, somehow it doubles every 40 minutes. Don't ask me how, that's sort of reserved for the engineers and the physicists out there to implement, this magical chocolate bar thing, okay? We have two parts here, right? Notice part A is asking us to write the question in terms of doubling time, and part B is asking us to write the model in terms of relative growth rate, right? And we can do this. You'll see that this is possible, and that's because, maybe you have thought this through a little bit on your own, but any exponential we can write in terms of another base so long as we scale the exponent correctly. And I'll kind of show you that in this, okay? This first one, right, is fairly easy, right, because we're given a doubling time, okay? So we have that n1 of t is my initial population of chocolate bars, okay, times 2 to my t over a, okay? Well, my t is that, and a is my doubling time, which is 40 minutes, so that's going to be 2/3 of an hour, so t over 2/3, but that's a strange way to write a fraction, so we can rewrite this as 10,000 times 2 to the 2t over 3. So for part B, there's a number of different ways to sort of go about this, okay? Notice that we have n naught on both of these, and 2 to the t over a, and e to the rt, okay? And here's how we'll do it, okay? Let's use n1 to generate a pair of values, okay? Before I grab that specific example, this should actually be 3 halves, okay? I don't know how I missed that. But let's see what happens when we grab a specific case, say n1 of 2/3, okay? Well, if t equals 2/3, well, that's precisely our doubling time, right? 2/3 of an hour. So we should have 20,000 bars, okay? But we also know, right, that these two models should agree for every input, right? So that means n2 of 2/3 should equal 20,000 as well, and that's my n naught, which is 10,000, e to the r, my rate of 2/3, okay? And now I have an equation strictly in terms of r, and I can solve for it, right? We're going to get from this e to the r times 2/3 equals 2 by that division. Taking the natural logs, we're going to get that 2r over 3 is the natural log of 2, or that r is 3 times the natural log of 2 over 2, okay? And now that we have my r, I can write my expression n2 of t, which is 10,000 e to my r 3 times the natural log of 2 over 2 of t, right? And I think if you think about this expression a little bit, you might stumble upon a little bit faster way to convert between bases in this instance, noticing that we have an e, and one of the things that it's raised to is the natural log of 2. But I'll leave that for your own pondering, okay? Our next sort of large-scale model that we're going to have to work with, there's going to be 2 more, and they should go a lot faster than the other 2. We're just going to kind of touch on them, okay? Is that of half-life and radioactive decay. Okay. And here's what I want you to think of, okay? So say we have some chunk of some radioactive metal, okay? Say this little amoeba, say this is a chunk of thorium-230, okay? Thorium-230 has a half-life of 80,000 years, right? Which means that every 80,000 years, half of the thorium-230 will radiate away, okay? But notice that that's almost exactly the opposite of our previous model, right? Using the exact same ideas, we can model the half-life as this. I'm just going to call it M1, right? Maybe for the amount of metal left over is the initial amount of metal times 2 to the time divided by the half-life. But we do need to make a small change here, right? Because remember, our populations were exploding, right? They were doubling. But the thing we're interested in is decaying. So that means we need a little negative sign, right? And that's our model for the amount of metal left over given a specific half-life, okay? And we're interested in, just like with the population, we're actually interested in looking at something like this, okay? Just because, again, these exponentials are so incredibly useful. And so here's what we want to do. Again, we want to kind of follow what we did in this last example and solve for r, okay? So what happens if we put in our half-life, right? Well, if we put in our half-life, then our output should be our initial amount divided by 2, right? That should also equal this guy right here, right? So it should equal the amount of the initial amount of metal times e to the minus r times h, right? Because we're evaluating at a specific time. But look at that, right? We can cancel those 2 m naughts, and we get e to the minus rh equals 1/2. Taking natural logs, we get minus rh is the natural log of 1/2, okay? Or r is the negative natural log of 1/2 divided by h. Now this is a little bit ugly, so I do want to switch it up just a tad, okay? Notice that the natural log of 1/2 is the natural log of 2 to the negative 1, right? Which is negative the natural log of 2. So I can write that my rate is the natural log of 2 over h, very, very similar to what we got here, okay? So that means that if you want to model in terms of E, right, because half-life is more commonly what we actually are able to measure versus, some sort of like relative scaling, right? But you still want to use the base of e, right? Because again, as I've said, the base of e can be very, very useful. Well, that means that I can write my equation like this, right? I guess I'll write them both down. We have m1 with a base of 2, and we have m2, m naught, e to the minus natural log of t over h times t, okay? These are our two handy models for radioactive decay. So let's do an example of it, okay? So we have the polonium-210 has a half-life of 140 days, okay? Suppose we start with a 300 milligram sample and we have questions A, B, and C. First, we want to create a model using our two forms, M1 and M2. Then we want to find the remaining mass after 1 year. Then we want to ask how long before the sample has a particular mass. Okay. So let's start with question A. Recall that our first model is m naught times 2 to the minus t over h. Okay. And thankfully, well, what? We have an initial mass of 300 milligrams, 2 to the minus t over 140 days being our half-life. Then, similarly, we have m2 is m naught e to the minus t natural log of 2 over h. And just like that, we have minus t natural log of 2 over 140. Okay, just like that, we have our models. Okay, for part B, we're interested in finding the remaining mass after 1 year, right? And that's simply asking us to plug in 1 year into our model and then go from there. Okay. For part B, I don't know, let's use M1 of t. Okay. Copying down our model, since we're on a new page and we don't want to forget, 300 times 2 to the minus t over 140. Okay. Well, B is asking us for M1 of 365, which is 300 times 2 to the minus 365 over 140. That right there is our answer, right? This is an exact form, right? If this were on a quiz or a test, this is what I would be looking for in an answer, okay? For those of you who are calculator curious, well, then this is about 49.26 milligrams, okay? Part C, we're being asked how long before the sample has a mass of 200 milligrams, okay? Which means we're looking for a value of t where it outputs 200, okay? I'm going to use my second model here. So where does m of t equal 200, right? Copying down m of t, we have 300 e minus t log 2 over 140. Dividing by this 300, we have e to our minus t log 2 over 140. That's going to equal 2/3. Taking natural logs, we're going to end up with minus t log 2 over 140 equals the natural log of 2/3. Okay? And then we're going to do some multiplication and find that t is equal to minus 140 times the natural log of 2/3 all over the natural log of 2. Once again, this is our exact solution. If you run it through a calculator, you get about 81.9 days. I only have one more model for you, and it will be by far our shortest discussion. And this one is called Newton's law of cooling. Okay. And Newton's law of cooling states that the rate at which an object cools is proportional to the temperature difference between the object and its surroundings, right? Which is, makes sense, right? If you have a hot thing in a cold room, like the relative difference of that is going to be how quickly it cools. And if you take that statement and you hand it to some calculus and you let the calculus do its job, we get out the other side this equation, okay? Provided that the difference in their temperatures isn't too extreme, okay? We get that our temperature is a function of time. That's the temperature of my surroundings plus the initial difference of temperatures times E to the minus KT, okay? Once again, going over these constants, that's the temperature of the surroundings. That's the initial difference. Okay. And K is a constant dependent on the object, and K is strictly positive, right? Okay. So let's go to the next page for an example of this guy, okay? So we have our cup of coffee, starts at a temperature of around 200 Fahrenheit, it's placed in a 70-degree room, and after 10 minutes, the coffee is 150 degrees Fahrenheit. We're asked to find a function modeling the temperature of the coffee over time, okay? We want to find the temperature after 15 minutes, and we want to see how long until the temperature of the coffee is 100 degrees. Personally, I think 100 degrees is a little bit cool for your coffee. I like mine more around 120 degrees, but that's neither here nor there, okay? So let's take a look at these, okay? So let's start with part A. Starting with what we can, okay? We know that my T of T, right? We know our initial temperature of the surroundings, okay? We know our initial difference, right? Our initial difference is, well, 200 minus 70, okay? So we'll write that down. And then we have e to the minus kt. So we're starting with 200 plus 130 e to the minus kt. And we're interested in finding k, right? Like right now our goal is find a value for k. And we can do that because we know that after 10 minutes, the coffee is 150 degrees. So that means that 70 plus 130 e to the minus k times 10 equals 150, okay? Now if I subtract 70 and then divide by 130, we're going to get that e to the minus k times 10 is 8 over 13, okay? Taking our natural logs, we're going to get that minus k times 10 is the natural log of 8 over 13, or that k is minus 1/10 times the natural log of 8 over 13, okay? I'll rewrite that equation on the next page just for the sake of room, right? The temperature of my coffee is a function of time, is my temperature of the surroundings plus the initial difference times e to the minus t times our value of k, which is minus 1/10 times the natural log of 8 over 13, okay? And that is our big equation, okay? Part B is now nice and simple, right? What is the temperature after 15 minutes? Well, the temperature after 15 minutes is precisely 70 plus 130 times e to the minus 15 times minus 1 over 10 times the natural log of 8 over 13, right? This is the answer, right? It's not very clean, but it is exact, okay? Turns out it's about 133 degrees Fahrenheit. Again, a little bit warm for my taste, but such is life, right? Coffee is never quite the perfect temperature, I've found, okay? And now for our final, we're looking for the time where we dip all the way to 100. Okay, we have 100 times 70 plus 130 e to the minus t times minus 1 over 10 times the natural log of 8 over 13. Okay, and this right here is directly solvable using methods that we discussed earlier in this lecture. So I will leave the rest of this question for you to work out and see just how long it takes for your coffee, assuming that it's in these situations, to drop to 100 degrees. And with that, we've actually wrapped up all of Chapter 4. Remember that you do have a test on this content next Wednesday. So make sure you're studying and reviewing for that. As such, there won't be a lecture next Tuesday, right? You'll kind of have that time to study. And then the following Thursday, we'll start some new content.